All right, we are looking at topic 1-4 today. It is angle pairs is what we're looking at. Pairs of angles. We all know that a pair means you have two of something. And so when we look at angle pairs, we start off by talking about adjacent angles. Adjacent angles are what you get when you have two coplanar angles. They share a common side, they share a common vertex, they do not share any common interior points. All right, so we throw out a little bit of a common sense question here. What is an interior point? Well, an interior point is on the inside of the angle. That's a point that is in between the two rays, would be an interior point. All right, so here's a couple pictures of adjacent angles, a couple of good examples. Okay, you can see that angle 1 and angle 2 have that side right there in common. And they also have, right here, they have that vertex in common. Same thing going on with angle 3 and angle 4. They've got the vertex right there, and they've got that side in between them is what they both have in common. Now, something they don't have in common would be the space that they take up. So if I took this point right here, that's on the interior of angle 3, but it's not on the interior of angle 4 because it's not between those two rays. Same thing right here. This point is on the interior of angle 1, but not on the interior of angle 2. So adjacent angles, they have a shared side and a shared vertex, but they don't share any of the space that they take up. The next pair of angles we're talking about would be vertical angles. Vertical angles are two angles whose sides are opposite rays. And if you'll remember back, opposite rays means that when you put those two opposite rays together, they form a straight line. So vertical angles are what happens when you have angles that are on opposite sides of where straight lines cross each other. Okay, I direct your attention to this picture right here where angle 1 and angle 2 are vertical angles. Angle 1 has a side that goes right there where that green line is. Okay, angle 2 has a side right there that is an opposite ray. Okay, that side of angle 1 with the green line and that side of angle 2 with the orange line are opposite rays. Okay, same thing on the other side. That side of angle 1 with the green and this side of angle 2 are opposite rays. So angle 1 and angle 2 would be vertical angles. Next thing we're looking at is complementary angles. Okay, by the way, if you need to pause the video to finish drawing the pictures of stuff, go right ahead. I don't care if you're actually watching this all the way through in one go. It doesn't matter to me. Complementary angles are two angles whose measures add up to 90 degrees. Okay, so there are two ways you can get this. One of them is like the picture that's on your right. Angle A and angle B are not connected to each other in any way, but those two measurements, 47 and 43, add up to 90 degrees. On this other picture, the one on the left, the reason we know that angle 1 and angle 2 add up to 90 degrees is because of that little fella right there. That little square in the corner tells us that the whole entire thing, this whole entire angle altogether, is 90 degrees. It's a right angle, okay? And we know from angle addition that angle 1 plus angle 2, when we add those measurements together, it equals the measurement of the whole entire thing. So angle 1 and angle 2 are adjacent angles. You can see that they have this red ray. They have that in common. They've got the vertex down there in common. And they don't share any space. When you put them together, what you have on the left-hand side of your paper, you have two angles that are both adjacent and complementary. They form a right angle. The last pair of angles that we talk about is supplementary angles. Supplementary angles have a sum of 180 degrees. Okay? Look at these examples of supplementary angles here. All right? When this talks about angle B and angle C, that's talking about this C and the same angle B as in the previous set. Okay? And that's another example of two angles that aren't connected to each other, but their measurements add up to 180. 137 and 43 add up to 180. The other picture, angle 3 and angle 4, is much more common. Okay, and angle 3 and angle 4 form what we call a linear pair. And on your paper, the linear pair postulate says if two angles form a linear pair, they are supplementary. Okay, let's talk about this. A linear pair is what happens when you have two angles that are adjacent, so they share a common side and they share a common vertex. But when you look at the sides of the angles that they don't have in common, this side right here and this side right here, when you put them together, it forms a straight line. Okay, that's what a linear pair is. So on the left-hand side of your paper, if two angles are both adjacent and supplementary, what they form is a line. So on the next slide here, the next part of your paper, it has a picture printed on there, and it's asking you to use that diagram to figure out if the following statements are true or false. Okay, so what that first statement says, we're dealing with angle AFB and angle EFD. AFB is highlighted right there in yellow. EFD is highlighted right there in blue. And it's asking the question, are those two things vertical angles? Well, if we're dealing with vertical angles, we have to ask ourselves about the sides of that angle. Okay, the way we defined it up above on the paper was that it's two angles where the sides are opposite rays. So when I look at the side of this angle, FA, and I look at the side of this angle, FD, that definitely forms a line. So that's definitely opposite rays. However, when I look at this side, when I look at FE, that is not an opposite ray with FB. Okay, that ain't gonna cut it. So what that means is that they're not opposite rays, and so this right here is a false statement. They are not vertical angles. Take a look at the next one. The next one is angle BFD. Angle BFD and angle CFD. There's BFD in yellow, and there's CFD in that sort of pink. All right? And it asks, are they adjacent angles? Well, I look at our definition of adjacent angles that we wrote down up above. We see that these two angles do share a common side right there. They do share a vertex, that point F right there in the middle. But that third thing is talking about interior points. What I'm going to do right now is I'm going to shade the interior of angle BFD. All of that space right there is all the interior of angle BFD. It's what's in between the two rays. Now what I'm going to do is I'm going to shade the interior of angle CFD. Again, it's all of the points in between those two rays, all of the space in between the two rays. Y'all see how much of that is crossover material? Okay, what that means is all of that area that got shaded by both colors is interior points that they have in common. Y'all, adjacent angles have no common interior points. This is also a false statement. With all those points they have in common, they could not be adjacent angles. Looking now at that last statement, The very last statement is asking about angle AFE and angle BFC. And it's asking, are those two angles complementary? Well, we already know that complementary means they add up to 90 degrees. So we ask ourselves, what is 62 plus 28? And it's 90. Y'all don't make it harder than it has to be. The sum of those measures is 90 degrees, so this right here, true statement. The last thing at the bottom of the paper is asking you to name two linear pairs. There's a lot of different answers. Okay, y'all can see on that diagram, there's a lot of different points. There's a lot of different rays coming out of those points. And so what I'm going to do is I'm just going to pop up three correct answers for this question that ask you to name linear pairs. Okay, the first one is going to pop up is this right here, angle EFA and angle AFC. Okay, take a look at this. These two angles have this ray in common. Ray FA is something that they have in common. When you put them together, they share that side and they share the vertex down here in the middle. But the sides that they don't share is what we're focusing on. The sides that they don't share form a straight line when you put them all together. And that's what makes these two angles a linear pair. Okay? It's the same thing with our next linear pair. It's the same exact thing with EFD and DFC. Look at this. EFD goes like that. DFC follows this pattern right here. You can see that they have this ray, they have they have FD in common, and the other two sides that they don't have in common line up together into a straight line. So that would be a linear pair. Our last one is EFB, angle EFB, and angle BFC. BFC there. Okay, you can see very clearly what they have in common right there. And you can see what they don't have in common forms a straight line. So there you go. All of those are angles that are linear pairs. All right, this next problem asks us, we're on to the back of the page now, the very back of the notes packet. And we see that angle KPL and angle JPL are a linear pair. So first of all, we look back at the linear pair postulate that says if two angles form a linear pair, they are supplementary. Okay, so if we have two angles that look like this, okay, step 1 on your paper says to find x. I'm going to go ahead and insert step 0.5, and that is to draw a picture. I read the other day that 68% of learners are visual learners. So as nice as it is to see that information written down, and as nice as it is to hear me reading it out loud, drawing a picture is going to be a lot more helpful in this situation than any of that, at least according to the stats. So we have that KPL and JPL are a linear pair. So they have one side in common. That's this side right here. PL they have in common. And the other two sides that they don't have in common form a straight line that goes right across there. All right. So we also know that a linear pair means the angles are supplementary. So by that definition, we can take the two angle measurements, and if we add them together, we will get 180 degrees. So I guess the question is, what do we know about the angle measures? Well, unfortunately, the only information we have is those two things right there, 2x plus 24 and 4x plus 36. So we're going to have to find what x is if we're going to deal with anything. Okay, we plug in those two expressions, and after that, it's just solving an equation like you've done 100,000 times since 7th grade all the way through right now. You combine like terms, and then you subtract to get the x's by themselves, and then you divide to get rid of the coefficient. We end up with x equals 20. Y'all, that is not the end of the problem. On every single district common assessment that I've ever looked at for geometry, there is a problem that asks you to add stuff together like this. Add together expressions like this and like this. And one of the answer choices, almost every single time, one of the answer choices is whatever x is equal to right there. That is not helpful to us, okay? That is not what the question is asking for. The question doesn't care what x is equal to. The question wants to know, what are these angle measures? Okay, how big are those angles? And to find that, we have to plug in x into the expressions. So 2x plus 24 becomes 2 times 20 plus 24. 4x plus 36 becomes 4 times 20 plus 36. Okay, and we end up with 64 and 116. So the question is, how do we know if those are good answers or not? And the answer is this. If we add these two things together, 64 plus 116, well, that is equal to 180. Okay, does that make sense with what we know from the beginning of the problem? Yes, it does. Angle KPL and angle JPL are a linear pair. That means when you put those two together, it forms a straight line. Y'all, a straight angle has 180 degrees. So our two final answers should add up to 180 degrees. So we've got two good answers. Good job, us. Nailed it. The next thing is what's called an angle bisector. Okay, we start again just like we did the other day with that word bisect. That word bisect, just like we talked about before, means to cut in half. It doesn't mean just to cut into two pieces. It means to cut into two pieces that are the same size. So when we talked about it before, we talked about segment bisectors. Segment bisectors were things that split a line segment into two evenly sized chunks. An angle bisector divides an angle into two congruent angles. So instead of dividing a segment into congruent segments, we're dividing an angle into congruent angles. Okay, all that means is the bisector is what splits an angle into two evenly sized smaller angles. Look at this example. You can obviously tell that angle 4 and angle 6 are congruent to each other because they're both labeled as 41 degrees. Okay, of course they're the same size, and what that means is that this ray, UK, that is a bisector of the larger angle. This next one is a little bit less obvious. Okay, how can we tell that angle 3 and angle 5 are the same size? And the answer is this. Y'all remember when we talked about segments, and if you had one segment that looked like that and it had two hash marks through it, you had another segment over here with two hash marks through it, then that meant those two segments were the same size. Okay, angles are done the same way, but instead of putting hash marks through stuff, you put rings around the inside of the angle. On the inside of the angle, angle 3 and angle 5 both have one ring that I just traced over. Okay, and that means they are congruent to each other. We have one last problem that uses the definition of an angle bisector. Okay, it tells us that ray AC bisects angle DAB. First of all, I want to just take a minute on this sentence right here. If you have never taken a geometry class and you see that sentence written down on a piece of paper, that does not make any sense at all. Okay, you're trying to read through that and it says air conditioning, for some reason has an arrow on top of it, and bisects, you may or may not know what that word even means. And then for some reason, the word dab is capitalized and it has a little squashed L in front of it. Okay? If you're outside of a geometry class, that makes absolutely no sense at all. But us, being the brilliant, very smart, very brilliant geometry students that we are, we know exactly what this means. What this means is that we have an angle, and that angle is called DAB, and the vertex is A because that's the one that's in the middle of that angle name. And there's also a ray that comes up in the middle of this angle, and with that word bisect, we know that ray AC splits it up to where these two angles are exactly the same size. So they're both going to get one ring. Okay, the next piece of information says that it's 58 degrees in DAC. Y'all, we got this entire diagram all right here from 2 sentences, just that and that right there. Okay, so don't tell me you never learned anything in school. That's what this is. The diagram that the textbook gives us is exactly the same as what we just drew up on our own. Because in geometry class, we didn't learn nothing, we learned things. All right, so 58 degrees. This is a classic example of a problem that you need to not make too complicated for yourself. Okay, the definition of an angle bisector means that the two smaller angles, this angle that's labeled as 58 degrees and this angle that doesn't have a label are the same size. Okay, since ray AC is a bisector, that means those two smaller angles are the same size. So the other one must also be 58 degrees. And if the question is asking for the measure of the entire thing, the entire large angle, what I just highlighted in pink right there, then all we're doing is we're adding 58 plus 58. Don't make this harder than it has to be. Y'all, in geometry, there are a lot of things that seem like they're very complicated, and they're really, really not. Okay, this is a very good example of something that seems like it's a lot, but it really isn't. Okay, so don't stress yourself out trying to fly through this thing and acting like you don't understand and you never will, because it's really, really not so bad. All right, it's going to be okay, and I am positive that everybody in this class is going to do just fine. No trouble at all. All right, that is the end of our notes on this lesson. When you're going through the homework problems and you see anything about the words shaded region, when you see shaded region, you do not have to do those problems. Skip them. All right, that is all we have for this lesson. Y'all have a good day.